This is the 16th video in the video series of Orbital Mechanics with Python. This one, I'm going to be going over how to plot the orbits of all the planets in the solar system using Spice files. And this is going to become useful when we go ahead and do the n-body problem and solar radiation pressure. So first, I'm going to go over what Spice files are going to need for this. As I talked about in the last video, the SPK files are for ephemeris, LSKs for timekeeping, or the leap seconds, and then the metakernel I'm going to go over here. So I'll go half and half here. So what we want to do, I'll go to this. So as I talked about in the previous video, I made a Spice data folder where I have some Spice files that I downloaded from the NASA website, which I guess I'll just post a link to it again, just to have it in both places. So first, we're gonna have the SPK file, which I showed in the last video, has all the data of all the planets, which I guess I'll just do it again. So if I go exe tools, and then we'll go brief, and then spice data, DE432, that'll auto finish. I'll make this a little bigger. But basically, we have all the data of Mercury to Neptune of the very center of these systems. Jupiter's in there, and Pluto as well. From 1949 to 2050. So we have those files, which I wanted to show, and I'll show the Python in a second. Just want to get this out of the way. And then LSK, so if we ls the spice data again, this latest leap seconds just kind of keeps track of time, which is something you need to load in where you're running these, which I'll explain in the metakernel, I guess. So the metakernel, is made so if you didn't have a metakernel file, in your Python script, you'd have to load each spice file individually. But if you have a metakernel, you can just load everything at once, which I have here as a solar system kernel.mk, where mk stands for metakernel. And I will get to that very specific syntax, which I guess I can do now, or we'll just get to the Python. So this is what that solar system.mk file looks like. It's going to be very specific, and you want to follow this exactly. Because this is just the way they decided to format the metakernel files. So you need this /begin data, kernels to load, just literally exactly the same way. Make sure it's in parentheses. And then each file in here is going to be the path to whatever spice file you want to load. So in this one, I have latest leap seconds, which does the timekeeping, and D432S, which has all the ephemeris data. And then /begin text. I think you could just put whatever here, doesn't really matter, but I have no need to put anything, so I don't do it. And so that's what the metakernel is. And again, very specific syntax. You're going to want to follow that exactly. And we're going to get to the spice tools. So now I'll get to kind of the SpicyPie and how it works. So here are the spice tools. Here's the spice tools file. So I guess I'll show this real quick. I created a new where we go to Python tools, so we go ls Python tools. I create a new, ignore all these other things, but we have spice tools.py. So in the same place that tools.py is, put spice tools.py. So you can just import it all the same, have the same added path variable. And we're going to go import SpicyPie to spice, which actually I'll real quick get to the import. So Python 3. I'm going to do this in Python 3 from now on. I haven't been in the past, but I will from now forward. So if you don't know these commands, so Python 3 or Python, whatever you're using, -m pip install SpicyPie. If everything works right with your pip, this should install SpicyPie. I already have it installed, so that's what it's going to tell me. But if you don't have it installed, this is how you should do it. And if everything is, if you have the right version of everything, it's going to be fine, and it should it should install right away. Yeah, so requirement already satisfied, SpicePie. So that's how you would do that. So we have here import SpicePie spice, numpy is np, usual. I have this function where I'm going to put this side to side just so you can see, but I'm going to call this, technically it's V16, but it's the same thing. So what we have here, I guess I'll start with the main file that you're going to do. The same thing, path.append, the Python tools, which is why I put the spice tools in the same place as the tools.py, because you still have the same command. You can import both. So you have tools as T, and then import spice tools as ST. Just kind of make a little difference there. So I'll explain the rest of the script in a second, but I'm going to pause it here. And in Python, if you say exit, you'll get out of the script, wherever that gets called. So I have this function. So first of all, so import SpicyPie as Spice. You're going to need that to do all the I/O with the Spice files. And then, so right here, you load the metakernel for the solar system. So as I said before, if you have all your files that you need in one metakernel in this syntax, then you can just call it once. So if I didn't have this, I would have to load each of these two Spice files individually. But since I just put in a metakernel, I can just load it once, point it at where it needs to go, and it does it. And then I have this function here in ST, which is Spice Tools, which is my own library. I just call it getObjects. So getObjects is basically means, I'll put it side to side, but the way that I use brief as an exe tool, you're going to get all the whatever bodies, which I call objects because I guess they're objects in the SpicyPie sense, but you get the objects of the file, and you basically get the objects of the file, and you get the what do I call it? I call it the time coverage. Yeah, I call it the time coverage. Yeah, so you get the name of each object in the file and the time coverage for each. Well, the time coverage is how long it spans over. So this is the get objects file. So first thing you do is Spice, so import Spice, SPK. So SPK is the name of the file, which is if you go back to the cheat sheet, the ephemeris files they're in the SPK folder, but are .bsp files, which is shown. I'll scroll over here. Right here, BSP. So BSP is ephemeris file, but they're called SPK. Again, I don't know why. This is what they did, but SPK OBJ, SPK objects. So get all the objects from whatever file you're calling, which in here I call that DE432s.bsp file. So I want to create a bunch of empty lists where you have the IDs. So actually, I'll pull this up side by side because this might be helpful. If I go side by side here and go to the exe tools. So what we have here is the IDs, where the IDs are just a number. So Mercury barycenter is 1, Venus barycenter 2, Earth barycenter 3, blah, blah, blah. You can kind of get all those. The names are literally the names, so it would be Mercury barycenter, Venus barycenter, Earth barycenter. And if you don't know, barycenter is the center of mass of a system. So the Earth barycenter, I think, is still within the radius of the Earth, but it's the center of mass between the Earth and the Moon. Whereas, say, Jupiter has a bunch of moons, so it's the center of mass of all the system put together. TC sec, which TC is time coverage, so TC is plural, and then seconds, and then you can have it in calendar as well, which I'll show here. But basically, there's just 4 empty lists, a counter, and then display, which actually, I'll just run this real quick, because you can see the output as it's happening. So I have exit here, so if I run Python v16, oh, I need Python 3. As I said, I'm doing Python 3 from now on. Scroll this over. I'll make this full screen just for 1 second. So what we have here, which when I call this getObjects function, this is what comes out. So you have your ID, which is 1, Mercury barycenter, 2, Venus, and all that. And then TC for time coverage, you have from 1949 to 2050, which we already knew from the last video. And you have all these, basically. So that's what this is outputting. And then in order to do that, I just want to show that side by side. I know this is formatted very poorly, but when we get here, so if you want to display all these, which I said true in the other scripts, so print object, and then for each object in objects, get the ID. So when you get these objects, it's just going to give you a bunch of names of each body, which are strings. So you just add it to the list. And then here's another Spice function. Honestly, kind of forget what that stands for. WNFETD. SPK. So SPK again is the ephemeris file, and then COV is for coverage. And you have the file name, which we have passed in, and then which ID for that. So the reason that you want to get these objects is because this function gets the coverage from a file name for a specific ID, where the ID say is 1 for Mercury, 2 for Venus, and all that. And WNFETD. Here we can just, I guess this is a good segue for the documentation. WNFETD. They have some really weird names in here. Fetch a particular interval from a double precision window. Honestly, I can't explain it to you much more than that, but it's kind of just this function that is used. You can just copy and paste this, and then you'll get kind of this output that you're looking for. Where I'll show you why this output is kind of useful when I get to the main script. So here where you get the time coverage in seconds, and these are seconds since J2000. It's just kind of a standard that is made where J2000, you take it as an epoch, and then you get the seconds from that. So there's this other useful function in Spice called TIM out, where you have, this is a list comprehension, so I'll explain that. So you can give it this formatted date. So you have year, month, day, hour, minute, seconds, TDB. I forget what TDB stands for, but I guess I'll pull that up. Tim out, which is vectors routine input from TDB seconds and TDB blah blah blah. Yeah, so basically just converts from seconds from J2000 to kind of a human readable format. So we have, and then a list comprehension, if you don't know what it is, it's just a way to do a for loop in one line, so you can see the brackets here. So the output of this is going to be a list, and it's going to convert for each value in TC seconds. So for each time coverage in seconds, where you have 2, because this will give you an output that looks like this. So say like 1000 to 2000. That's going to be this output. It's just basically the beginning and the end from J2000 of where the epoch is beginning and then where it's ending, where the time coverage is beginning and ending in seconds from J2000. So it's going to give you a tuple. And then, so for each one of those, convert it to this kind of human readable calendar format. That's what this is doing, this line. And then append the time coverage just to output list, because sometimes you want the seconds, which I'll show you in the main script, and sometimes you want the calendar just to kind of see when you display, actually. This is what you do, the calendar, because it is more useful for us to be able to see these calendar days other than seconds since J2000, because we have no idea what that means. So 1949 December is much more readable for us. So we have that, and then get the name of the body. So there's this other function, which I kind of put a wrapper into. So to get the name of the body. So as of here, you only have the IDs, which is 1, 2, 3, or 300, whatever the body happens to be. And then if you want to get the human readable name, you have to go ID to body, where I call it ID to body. I made this function just because it's more intuitive than bod C2N. So I forget what C2N stands for, but yeah, basically it's a lot more intuitive to say ID to body than that, at least in my mind. You don't have to do this if you don't want to, but this is all that it's doing. Return the name of a body given a Spice ID. So you give that, and then if it comes up with an error, which means it doesn't recognize the body ID, then so you try, and then if it comes up with an error exception, you catch it, and then you do unknown name, which does happen from time to time if you get some kind of arbitrary bodies that aren't like one of the big celestial bodies, which is totally fine. And then if you want to display, which is an optional argument here, defaults to false, a bunch of string formatting. If you don't know what this is, this modulo I just means you have an integer coming in, which is the ID, and then -t is a tab. So -t, 2 tabs, -s is or modulo s is a string, -t, time coverage. That basically just, and then modulo s is just strings, which just maps. All this is doing is formatting this kind of nicely. It could have been done better, obviously, with one more tab, but that's all it's doing. It's kind of just formatting it, which isn't totally necessary here. And then we're going to return everything here. So how you use it in a script, which is what I'll get to here. So here, furnish, again, I already explained this, but furnish is just one of the Spice functions that kind of loads in the kernels. In this one, you want to load in the metakernel, so it loads in more than one kernel at once. And then I call this function getObjects, and the display equals true. And that's what comes up with this output right here. Just if you just wanted to know that, then there you go. So I'll take out this exit command. So as you can see in this, So I have Mercury, Venus, Earth, and barycenters, and then Mercury, Venus, Moon, Earth, which are not the barycenters. So for the sake of this, as far as plotting all the planets and be able to do it in a nice for loop, I'm only going to do the barycenters. So the names here that are output from the get objects names here, I'm only going to include the ones that include barycenter, just for the sake of kind of doing this in a nice for loop. And so again, list comprehension. If you don't know those, actually, I'll post a link to list comprehension because that's kind of a nice little Python thing. Maybe other languages have it, but it's nice to use in Python. So that's what that's doing. So only include the barycenters, and then we're going to create a time array. So the way that you get the ephemeris data is that you give the spice function, you give an array of seconds from J2000. And at every one of those seconds that you give it, it gives you the ephemeris data back. So you have to create this array beforehand in order to get all the data that you want. So I have another function here that I call st or tc to array, so time coverage to array, which is right here. I mentioned this in another video, but the reason that I make this, so initialize the array with zeros and have this 1, where it's different if you don't have that 1. And I'm not going to get to it this video, and I mentioned it in another video that I will get to it. I think when I added the mass to the state variable for orbit propagator, but I'll get to another video. But it's literally just creating lin space, so from the first time coverage to the last time coverage based on however many steps, where the steps that are passed in are going to be the same for all of them. So for all the bodies, and I just arbitrarily made it what is that, 100,000? Yeah, 100,000. Actually, I can make it 10,000. It's totally fine. There's no difference in this. So 10,000 steps in between 1949 to 2050. That sounds like a very little for 100 years, but in the scale of what you're going to see, you can't really see a difference between those amount of steps. So then create an empty list. So I have this time array, it just has an array from the beginning to the end, which however many steps in between, and then create an empty list for all ephemeris data. This might look similar because in orbits, this is what you do if you propagate. I think I've done it in a previous video, but if you propagate a multiple amount of kind of ephemeris data, you put them in a list. So it's a list of arrays. So you're going to do the same thing here. And then this is where you can, so this is where you actually query the spice files for this ephemeris data. So, and again, I wrote you could call it a wrapper, pretty low-tech wrapper, but basically for name and names. So you get these names from the get objects, which is just the literal name, Mercury barycenter, Venus barycenter, Earth barycenter, and all that. You're just literally getting the strings of names. So for each name in those, you're going to append to this list right here, this function that I've written, get ephemeris data. So I'll first explain this, the way that SpicyPie has this implemented as this function called SPK. Again, you can see all this SPK, so SPK COV, SPK OBJ, SPK EZR. I forget what EZR stands for, but this is how you get the ephemeris data. So I'm actually going to pull up the documentation to this side by side. You see a direct, see if I can move this over. So and I'll post a link to this documentation page because it's actually super helpful. You can kind of just Control F something that you want, and then they'll have a function for it. So this SpicyPie SPK EZR return the state with precision velocity is what we want, the target body relative to an observing body, optionally corrected for light time. I'm not going to get into light time in this because I've never really needed to, but it's something. It's just an argument. So what you have is the target body name. So target here, ET observer epoch, which can actually be these times. That can be actually be an array of times. It doesn't have to just be one. You can use it as one if you want. And the frame. So what reference frame do you want it in? Reference frame of output state vector. AppCore, which is aberration correction flag. I have it as default as none. I've never had a reason to use it, but that's something that could be used in the future, obviously. And then observer, so observing body name, which I'll get to. So basically this function, SPK-EZR, given these inputs, will return whatever ephemeris data that you're looking for. And I wanted to show this, how you can kind of get a very brief explanation from this SpicyPie website, because this SpicyPie is a wrapper for all the C functions. Oh, where'd it go? There we go. Oh, yeah, it's a wrapper for all the C functions. So it's basically the SpicyPie is written on top of C. So what I want to get at is that they have all these functions, and for each of these functions, they have the actual C documentation linked right to it. So that's right here. So if you want a more detailed explanation as to what the inputs are, you can just go here. So return the state, so that's the same thing. So here's brief, so a very brief kind of description of what all the inputs and outputs are. So you have the state of the target, one-way light time, all that, but target body name, epoch, reference frame, all the same stuff, and then you get detailed input. So if you want to know what kind of data type you're looking for, and all that, you can go here to get kind of more detailed data. Where this correction, I have none as a default, but then you can have all these kind of corrections here that if you'd like to put in, and then detailed output as well. So yeah, so for us, all we need to worry about is those inputs. So from here, this is all that. This is get ephemeris data. I put it in an array, and then I get to 0 because it comes out by an n/2 array, but we only really want the ephemeris data, so I just put a 0 on there. You can see that detailed output, kind of for more details on that. But once you get there, it's actually getting pretty close to the end here. So you're just going to get the ephemeris data from each one, where we have the times is here as an array. The frame I define as ecliptic J2000. I guess I'll post a video on the difference between ecliptic J2000 and just J2000. It just has to do with the way that the Earth's axis is pointed with respect to basically the rotation of the Earth, the axis of that with respect to the orbit of the Earth around the Sun. Obviously, there's an angle there. That's why we have seasons, but that's a whole other thing. And then observer. So for this, I just made the Sun the observer, where you could have the solar system barycenter as the observer, which is because of Jupiter a little bit outside the radius of the Sun, but as you'll see in the plots where it doesn't actually matter for us, really in the large scale of things. It could if you want to get really detailed analysis. But then you just go plot and orbits, which I've shown before, where you have these R's, which is a list of arrays, names for the legend, which we have here, show plot equals true, AU equals true is just something I may or may not have shown in the previous video, but if I just have AU equals true, where usually it's false, if AU equals true, then just make the axes divided by kilometers to AU, where km to AU is defined here. That's just how many kilometers in an astronomical unit. That's all it's doing. So not too complicated. Where did that script go? Yeah, and just plot, I guess. So I already ran this, so I know it's going to run. But anyways, just run that. And I only made it 10,000 steps. So it has all those outputs. And then slowly but surely, we'll get the plot. Computer's really heating up here. So, yeah, these are the plots of the planets. Just with a nice simple for loop, you can get everything. It's running quite slow on my computer right now, but you can see the legends here. I only included all the barycenter inputs, so all the planets with the barycenters. I'll zoom in here for the sake of seeing Earth. And you can see the scale of the Sun and why I said it's not too relevant that we do the Sun barycenter as opposed to, or the solar system barycenter as opposed to just the Sun, because there's the Sun, and you can see how large these orbits are compared to the radius of the Sun. I'm not going to mess around with this too much, just kind of want to show how this works. You can see all the orbits. The only thing I wanted to show is that all the planets except Pluto are very close to being coplanar, or all the orbits of the planets are very close to being coplanar, where Pluto is actually quite a bit off, and I think it's one of the arguments against why Pluto should be a planet, besides that its moon Charon is pretty big with respect to Pluto because they orbit a center of gravity that is outside of Pluto's radius. That's another, obviously, debate, but you can see here how the inclination of Pluto is actually a lot, I guess, more inclined with respect to this frame than all the other planets. And the other thing I wanted to show is that Neptune and Pluto's orbits are much longer than 100 years. So you're not going to get to see all this in this Spice file. But there's other Spice files that span for longer. And also you could do an n-body propagation to go ahead and finish the orbit if you want to get more detailed analysis. Yeah, so that's that with those. And I think that's it for this video as far as the Python. So I covered that kind of. I wanted to get you guys familiar with how to use these SpicyPie, how to actually get ephemeris data from them. And I explained how SpicyPie is kind of a wrapper for the C-Spice. And now that that's all done, I can get to the n-body problem. And then after the n-body problem, we'll get to solar radiation pressure. But n-body problem seems to be a little bit more interesting. So now that you know all the positions of, say, the Sun, Jupiter, and the Moon, you can apply all those to your orbit around the Earth and see how the gravity from those applies. So yeah, so next video I'll get to back to orbit propagator and you can see how I implement all the SpicyPie stuff in the orbit propagator. So yeah, that's it for this video. Again, let me know anything too slow, too fast. This is a bit of a longer video, but it kind of needed to be done because, as I said before, I haven't seen anyone else cover SpicyPie on YouTube, so I kind of want to get more in depth into it. So yeah, just let me know anything too slow, too fast, anything else I'd see. And yeah, thank you for watching.